Hello everyone, you're watching the channel Learn to Earn for Life. In this video, I will discuss the sequence impedances of the power system components. The impedances encountered by the symmetrical components are dependent on the power system equipments, that is the generator, transformer, transmission line, etc. The impedance of the circuit element when the positive sequence currents alone are flowing is called as the positive sequence impedance. When the negative sequence currents are only present, the impedance offered by them is called as the negative sequence impedance. When the only zero sequence currents are flowing is called as the zero sequence impedance. The sequence impedances are required for the component modeling and analysis. Let us find the sequence impedances of a symmetrical circuit. Consider a three-phase symmetrical circuit. Let IA, IB, IC be the line currents in each line. These currents return via the neutral or ground impedance Zn. The voltage drops are computed as VA is equals to IA Z plus IN Zn. Here we can substitute IN as IA plus IB plus IC. So further solving this equation, we will get VA is equals to IA into bracket Z plus Zn plus IB Zn plus IC Zn. Similarly, we can also solve for VB is equals to IA Zn plus IB into bracket Z plus Zn plus IC Zn. We can also solve for VC as IA into Zn plus IB Zn plus IC into bracket Z plus Zn. In matrix form, these three equations can be represented as VA, VB, VC column matrix is equals to a 3 by 3 matrix, that is first row Z plus Zn, 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 and the second row as Zn, Z plus Zn, Zn, and the third row as Zn, Zn, Z plus Zn into a column matrix IA, IB, IC. Expressing the voltages and currents by their sequence components. Here you can observe what is VA, VB, VC. We can express this in terms of sequence components, as well as we can also express these line currents in terms of sequence currents. Further, when we substitute in this place and taking the sequence voltages at the LHS side, we will get VA naught, VA1, VA2 is equals to 1 by 3 into a 3 by 3 matrix 1 1 1 1 A square 1 A square A into another 3 by 3 matrix into one more, that is 1 1 1 1 A square A 1 A square into the sequence currents a column matrix. By solving the matrices at the RHS side, we will get, keeping the column matrix I0 I1 as it is, we will get a 3 by 3 matrix as the first row Z plus Zn 0 0 0 Z 0 0 0 Z. So this is the matrix I will be getting after solving. So by observing this matrix expression, we can write VA naught is equals to Z plus 3Zn into IA naught. VA1 is equals to Z into IA1, and VA2 is equals to Z into IA2. So above equations indicate that in symmetrical circuits, currents of a given sequence produce the voltage drops of the same sequence only. That is, the sequence impedances are uncoupled in the case of symmetrical circuits. By observing that equations, we can write the expression for zero sequence impedance as VA naught divided by A naught is equals to Z plus 3Zn. As well as we can also write the expression for the positive sequence impedance as, that is, Z1 is equals to VA1 divided by IA1, that is equals to Z. We can write the expression for the negative sequence impedances, which is represented as Z2 by means of VA2 divided by IA2, that is equals to Z. We can express these equations, we can express these all equations in terms of sequence networks. This is the positive sequence network, this is the negative sequence network, this is the zero sequence network, which are representing these three equations. Here, from these we can say that the positive sequence impedance is same as that of the negative sequence impedance, as well as the zero sequence impedance is much higher than the positive or the negative sequence impedance. So this is the explanation about the sequence impedances of the power system equipments. Thank you for watching the video.